Hello, I am Brennan de Raad and welcome back to Module C of the Mitigation of Climate Change course. In earlier videos about decarbonizing the industrial sector, we discussed the strong connection between industrial activity, heating requirements and CO2 emissions, and looked at options to increase the efficiency of unit operations and decarbonize heat sources. In this video, we will discuss the option of using waste heat to increase energy efficiency of a production site. To get an idea about the potential of utilizing waste heat, let us revisit our pulp mill example. Drying wet paper at the end of the production process accounts for about 80% of total heating requirements to convert pulp into paper. A schematic overview of this unit is presented on the slide. Here, heat in the form of steam is added to the drying section to evaporate water out of the paper. The evaporated water is absorbed by the hot air flowing over the wet paper and is vented towards the flue stack. The added steam condenses and it transfers its energy to the wet paper. The resulting condensate is returned to the steam generator. A quick energy balance of this unit shows that all heat added by the steam generator will be lost via the flue stack unless part of it is recovered. In this example, part of the heat is recovered by preheating the air and water in heat exchangers, abbreviated by HX. In this video, we will discuss how engineers must look at meeting heating requirements from a process level view and help you to ask the right questions when improvements in heat integration or energy efficiency are suggested. At the end of the video, you will be able to read a composite curve, which is a seminal tool used in pinch analysis to assess the heating integration targets of an industrial process, and use it to assess proposed changes to increase the energy efficiency of a production process. Before we start designing elaborate heat exchanger networks, we should first look at the concept of heat itself. Though we commonly talk about an energy crisis or an energy shortage, the first law of thermodynamics teaches us that energy cannot be destroyed. The quality of energy, however, is not a conserved quantity. Let's take the energy conversion in a slide as an example. Before the water falls off the dam, it has so-called potential energy due to its relative height. After it falls off the dam, this potential is converted into heat and the temperature of the water is increased. This increase in temperature is relatively small and will not allow us to drive, for example, a turbine, something that would have been possible before the conversion. The same principle holds for heat. Once it drops its temperature, it loses its value, as we can no longer use it to drive machines or processes. When we apply the principle of quality of energy to process units, we can come to thermodynamic cycles. And some thermodynamic cycles have already been introduced in this course. An example is the heat pump that was discussed in session 1.4 of the MOOC on transport and buildings. Another process on which the internal combustion engine found in most cars is based on. In both cases, heat flows from a high temperature reservoir to a cold one, just as a cup of hot tea that transfers its energy to the environment. The flow of energy in an internal combustion engine, also known as a heat engine, is depicted on the right side of the slide. Here we see heat flowing at a high temperature from a high temperature reservoir to the heat engine. The heat engine converts the heat into work and the heat of a lower temperature. The latter two we know from the rotation of the wheels and the hot gases from the exhaust. These thermodynamic cycles can be applied in three different ways. The first is to transfer heat without producing work. This is called a heat exchanger. A heat exchanger that we encounter daily is the radiator we use to heat our homes, as seen in the left picture. The second is to use heat to produce work, as we discussed in the previous example. And the third is by adding work to the process to transfer low temperature heat to a high temperature sink. And such a process is called a heat pump or a cooling device. And a daily example is our fridge, where heat at a low temperature is transferred to the environment at a higher temperature. Two heat exchangers are used in our example case. One for preheating the supply air that is fed to the drying section, and one to preheat the water entering the steam generator. identifying which connections should be made from an energy efficiency perspective is done with the help of pinch analysis. With this method, elaborate networks of hundreds of heat exchangers can be designed. Process engineers and energy technologists have been trained in this method, and the basis of this method is that all streams that release heat are aggregated in so-called hot stream, depicted in red. And the same occurs for all streams that take up heat, the cold streams, depicted in blue. The overlap between these curves shows how much heat can be recovered with the help of heat exchangers. Further integration of streams is limited by the so-called pinch point. The temperature difference between the hot and cold streams is at its minimum here. An even smaller difference will result in uneconomically large heat exchangers. There is a trade-off between the cost of heating and cooling and the material cost of the heat exchanger. And asking engineers about their assumed minimal temperature difference is hence a good place to start a discussion. A second thing the composite curves teach us is the existence of energy regions. Above the pinch point, heat is required, whereas a surplus of heat that must be cooled away exists below the pinch point. Using high temperature heat from processes above the pinch to heat processes below it will increase both the amount of heat required and the surplus. It is therefore unwanted, and heat exchangers must always be integrated within an energy region. The latter rule is known as the first golden rule of pinch analysis. Two others exist and are presented in the slide, and we must abide by these three golden rules to increase the energy efficiency of a production process. The appropriate placement of waste heat technologies also abides these three rules. Therefore, when we look at these technologies and we start again with the heat exchanger, we should transfer heat within the red area or within the blue area. And a heat engine should either use its own waste heat to supply heat above the pinch, or it should convert surplus heat into work. A heat pump can only increase process efficiency when it transfers heat from below the pinch to above it, thereby reducing both heating and cooling requirements. In summary, in this video we discussed the energy efficiency options that use waste heat. If we apply our knowledge to the case study, we come to the following technology options. 1. If we look at the composite curve of our case study, we see that there is an overlap between the heat requirements to form steam out of water and the heat that is available in the humid air. Still, a lot of heat is required for the formation of steam after disintegration. A heat engine could be an interesting option to supply this heat. Otherwise, the engine could try to utilize the energy wasted through the flue stack. Another option is to use this waste heat and convert it into a higher temperature heat with the help of a heat pump and reduce net heat and cooling requirements. Thank you for watching the video, and if you want to learn more about heat integration, please have a look at the assignments. Good luck.